Hello? Okay. Okay, great. Thank you so much. Okay, so it is our honor to have Georgia Gkioxari here with us today for the keynote. She is an assistant professor at Caltech in computing and mathematical sciences. Before that, she was at Meta as a research scientist with the FAIR lab for several years and produced many famous projects you probably know and love, such as Mask RCNN, Detectron, Mesh RCNN. She works generally in detection and 2D, 3D recognition, reconstruction, and also helped build PyTorch 3D. So we're very lucky to have her here. She also received the Pammy Young Researcher Award, Mark Everingham Awards, and yeah, is generally doing excellent work in AI 3D, and looking very much to hear you talk about what you're looking at for the future. Thanks so much.
Yeah, thank you. You can hear me, I think so. It's very nice to be here. And today I want to take you on a little journey of computer vision. So that's why I call it from pixels to percepts, the evolution of machine vision through AI. So the introduction was fantastic, and I think covered sort of who I am, but maybe very briefly. My name is Georgia. I'm now an assistant professor at Caltech, but it wasn't clear that that's what I was going to do. So first of all, I was born in Greece, born and raised, and then around 2010, when I was 23, I decided to move across the globe, landed in San Francisco, did my PhD at UC Berkeley. And then right off of there, I became a research scientist at FAIR for 6 years, where I decided that industry is not so cool and went back to academia to be an assistant professor and overworked and poorer, but happier. So, great. So throughout all of these years, I have actually been working on one thing, and that is computer vision. It was, is, and will be my passion. And so what is computer vision or machine vision? In order to describe that, I just want to forget about the machine part. Yes. Great. So forget about the machine part, and let's look at what human vision is. And I always like to do this exercise because I feel that sometimes we don't appreciate how bright and intelligent we are. And so all of you wake up every day, and without doing anything or spending any effort, you can actually see and understand. For example, just to make that a very concrete example. Oh, no. Okay, this stopped working. Oh. Take a look at this image right here. I'm very certain that none of you have ever been on this town, the street. You're not part of what's happening here, but you can all understand very easily what's going on. There is a woman walking away, carrying some bags. There's another guy in the middle talking to this woman that's sitting on this, what is that, like a chair, whatever that is, playing the accordion. They're talking to each other. You can tell that by just looking at this image. You've never been there. You don't know these people. And it's not just that. You can also see beyond the pixels. I was recently in Scotland. I ran into this wonderful mural that tells a story by just colors. There is a painting of Mona Lisa that has been a little bit, someone drew on it, and there's a boy pointing to another boy, probably blaming him. All this story coming from just pixels shown at you and your brain interpreting it. And that was also very well known. And the first example that led to this sort of trying to accentuate how brilliant our vision system is was from this experiment in 1944. It was really long ago. And with this video that was created that I want to show you, Okay, so you've seen enough, and I think that most of you understand there is a story here, and you're likely also very emotionally attached to some shapes as opposed to others. So what's going on is that there is a bully that is bullying another shape, and there is a protector, and they're trying to protect the victim from bullying. This is the story, but all you get to see here is flickering black and white pixels on a screen. And yet your human vision system not only understands the story, but also attaches emotions to what you're seeing by simply seeing black and white pixels. So this is another testament of how intelligent we are. And this intelligence and our ease of understanding our scenes by seeing is something that you use every day to accomplish tasks. This is your visual intelligence is what makes you drive this car, hopefully by not running over people, safely navigating the streets. So in LA, that is very challenging. So if you're successful at that, kudos to you. So this is exactly why we're intelligent beings. We see and we act and we accomplish tasks. So this is the motivation of why computer vision exists, and this is what makes me excited about it. And in that regard, and inspired by what we can do, the goal of computer vision research is to try to embed all of that intelligence into machines. So can we build machines that can see just like humans can? Grand goal, big goal. So the first thing we need to do is we need to operationalize this. So how do we attack this big problem? And so the first task that we thought as a community, actually not me, but way before me even, was to tackle a first task in this direction. And the first task is, can we make machines that recognize objects? So image comes in, object understanding comes out. And this is a task that has actually been studied for many years, over 40 years. There were initial attempts at this all the way back to the 1970s by researchers that were trying to understand how to best model objects. So there was a clear understanding that objects are complex. So how can we best model them? So the work from Mar and Nishihara, which is the generalized cylinder approach, that's try to decompose objects into cylinders, and their composition was creating objects. Or the pictorial structural work from Fischler and Eschlanger that wanted to get parts, attach them with springs, and those structures then create these more complex components. So that was all done a lot by neuroscientists back then, just to understand what is the best way to actually model objects. Now, at the same time, kind of from the same community, there were people that were actually looking at the brain. They wanted to understand how the human vision system works, what gets activated where, what's happening. And that's a big mystery to this day, though we have done a lot of, there's more understanding today, but it all started with this experiment by Hubel and Wiesel back in the 60s, where the scientists were trying to understand, it's actually a very famous experiment. They were trying to, they found that single neurons in the cat's neural cortex fired when specific region of the visual field was stimulated. And that was the first time where we understood that there's different parts of the brain that fire when different structures have been shown, which is what led Fukushima later to develop the neocognitron, which is the first instantiation of our neural network. It's a neural net that recognizes image patterns by convolutions. And this is what Jan LeCun took a few years later and made it into a learnable representation, where now the convolutions are actually being learned through data, and in this case, for digit classification. So this is kind of how it all started, or it was the most pioneering work in trying to understand the human vision system. And I'm going to take you into fast forward to like today and show you what it is that our object recognition systems can do today. And I'm going to show you this video. Well, what you see here is you see a modern state-of-the-art computer vision system and object detection system that takes a single image of a scene that has never been before, and it can tell what objects it sees by outlining their box. It can understand human poses. either in a key point form or in a dense mesh form, and also outline the silhouette of objects more to localize more precisely. And it can do that with a variety of objects. You can even tell the confidences of its predictions. So this is quite a big improvement in only a matter of 20, 30 years, starting from neocognitron and pictorial structures going all the way to these modern detection systems. And this is work that's all featured in Detectron 2, so it's open source and you can all download it, which is another great characteristic of our community. But the ideas actually kind of remain the same. We just figured out how to make them work. So what you saw here before was a model that's called Masker CNN. It's a neural network. It takes as input an image, any image of any objects, any number of objects. It processes it through some operations stacked one after the other, and then the output is the recognition of the objects and their types and also their silhouettes. And while we can get into a lot of the details and what makes this work and how you can build such a system, the two main driving factors are the following. So first, we have a very large neural network. So what was shown before as just a small little rectangle, three-dimensional rectangle, is actually a 150-layer CNN. So these big neural networks, again, going back to neocognitron and Jan LeCun, we figured out how to make them very big and thus very performant. And the other important part that actually is very relevant to this day is the concept of learning from data. So it turns out that if you want to teach these models how to understand objects, all you have to do is show them positive examples of the concept you want them to pick up. So you have, you want to teach the model what a cat is, you just show it a few examples of a cat, same for dog. And what is also important here is not just positives, but also negatives. While you give it positive examples of a cat, everything else that's not a cat is a negative example. And just this simple realization led to us understanding all of these concepts very well so that we're able to understand it. And thanks to the internet and that revolution, we've been able to scale up these data collections and create data sets for many concepts so that the models can learn a huge variety of them. And the result is these systems that can recognize objects or under very challenging settings like occlusions, and also under settings like reflections, where here, luckily, the reflection of the human is not detected, which is great. And all of these models are actually tying us back to what we all thought all along, how we're going to recognize objects. So if you go and dig deeper into what our neural network learns and we train it from data and positive examples, if you go to the first layer, what you see is the first layer being the first operation, the simplest, starting right out of processing the data, is just a generic primitive structures like edges, corners, little like points of interest. We knew this all along. We've been working with Gabor filters for many years before neural nets. These actually look exactly like Gabor filters. And if you go deep into the network, you start seeing other things emerging. So in the nth layer of the neural net, you start seeing that certain parts of the objects do emerge. We have layers that activate for the faces of dogs or that part of the house structure. So what is this? This is nothing else like trying to decompose objects into simpler parts and then figuring out how to connect everything together, just like the Fischler and Eschlanger thought it would happen. But now this time, it just happens in a very end-to-end manner without us having to hand code this. The network learns itself to actually understand primitive of objects at parts and then compose them together in order to do this. And this has been a fantastic and very successful line of work. And we can't just recognize object, we can also recognize shape, poses of people. And these models work so well that you can apply them and frame by frame on a video, and you can get a very continuous result, very robust result. You can also do a lot more complex tasks. You can recognize human-object interactions. This is activity types and how humans interact with objects for a variety of interactions and a variety of scenes. This is a very challenging task. You can also track humans in videos with their pose. And this has been a revolution in 2D recognition that has led to an excitement in the community. It has also led to a lot of development of products. Models like mask recognition have been used in a lot of attempts for for self-driving cars, and of course, modern variants of it. But all of these methods have one big limitation. They actually treat the objects as if they were two-dimensional entities. But objects are not two-dimensional entities. They don't live on the image grid. They actually have shape. The shape is something that we know exists because our world is three-dimensional, but unfortunately, images are two-dimensional. And all of our computer vision attempts so far are trying to treat as if the world is also two-dimensional. And that is a limitation, and especially a limitation for a lot of the applications we want to build in the embodied space, where we want to build machines that actually interact in the real world. And so the second task after the first task of can we even understand objects is, well, can we understand objects in 3D? So image comes in, and I want to understand objects, but also their 3D attributes, their 3D properties, their shape, their geometry. That will be fantastic. That brings us closer to the real world and how objects actually are. But it's also a very challenging task because all you see is a 2D image, and you're trying to infer all of this richer properties of these objects that are not really visible there. So geometry and texture. You don't see the full-fledged geometry in the image. So this is hidden, which is a limitation of 2D approaches. But is this possible? And here's where learning can shine, as we can actually try to learn priors about our objects in order to solve this task of lifting from 2D images to 3D. But how was a big question. And especially how can we extend what we've learned from vision in the image space? So at this point, 30 years after Fischler and Eschlinger, we can finally say that learning with images is easy. We have our tools. We have PyTorch or TensorFlow, though PyTorch is better, just biased. We have our neural nets that are getting bigger and better and stronger. And we have our data sets that we're collecting. And at this point, they're getting like a huge billions of images as opposed to a few tens or hundreds, as was 30 years ago. And so we kind of have all the secret sauces, and now we can build things. But when it comes to 3D understanding, none of this is actually there. We have none of these tools available to us. And so when I started working in the space, I thought, well, maybe the first thing we need to do is actually need to build the tooling in order to even try to attempt to replicate the success of 2D and 3D. So that led to PyTorch 3D, which is a library for 3D deep learning in PyTorch with PyTorch. It offers modular implementations and operations that will allow you to bridge the gap between 2D imagery and 3D. And most importantly, it also gives you the way to deal with 3D data, which is not very easy. And so here's a cute little video that explains what meshes are. Hopefully, some of you know what meshes are, but they're definitely very different than images. And the challenges start very very fast, even at the stage of batching, where you have meshes that can be of any resolution, and how to batch them, which is very necessary for learning, is not easy. So we offer all of these things. You might think, oh, batching, really? No, yes, batching. If you want to learn efficiently, you need to have efficient ways of representing your data in a chunk of examples. And doing that turned out that was very, very important. A very critical operation in PyTorch 3D that will allow us to learn from 2D to 3D is this operation of rendering. So we are in a VR work conference. rendering should be something that you all know, yes? Okay, so what's rendering? So you take a 3D scene, you have your 3D shape, you have your texture, you have your camera. And the process of rendering projects us down to a 2D image. You see the results of rendering every day in your life. If you play video games, I'm sure all of you do, you see the results of rendering in real time every time. If you watch Hollywood movies that have a lot of visual effects, there's rendering involved here, rendering of 3D scenes to the image plane. So rendering takes a 3D scene, projects it down to an image plane. It's great. It's a great operation. It's a very complex one. But if we want to learn with it, only this is not enough. We need to figure out how to propagate gradients back from the image to the 3D properties of the scene. And how to do that turns out is also not very trivial. Differentiable rendering is a very non-linear operation, non-differentiable operation. So we need to make it into one if we're hoping that we can learn through this. And it turns out that it is possible. And there have been many attempts. So this graph here shows why rasterization, which is a part of rendering, is not differentiable. You have these X, Y, and Z discontinuities when you want to render shapes. But this is how we can make it this suggests how we can make it differentiable, and this is by basically making our 3D primitives transparent towards the boundary, and also blending multiple 3D primitives on array, and that turns these discontinuities, these X, Y, Z discontinuities, into ramps, which makes them much more friendlier for differentiation. And now that we have this differentiable rendering in place, and we can learn through 2D losses to update our 3D representations, that opens up a whole new world of possible optimization problems. And one of those we explored with my student at UC Berkeley, a student I collaborated with, where the problem here was to take 8 input views of an object, so not too many, a few views of an object, and lift those objects into 3D in both the shape and the texture. And the approach is a purely optimization-based approach here, and it's very simple. So you have your input views of your object, and you start with an initial shape. This is the generic initial shape that's very far from what the actual shape of the object is. And you are framing this problem as updating your shape based on 2 of the 3 input views, such that when you render the shape from the camera viewpoint of the 3rd remaining view, it actually matches. And what allows this model to actually optimize is the fact that when I'm comparing the 2D images, I can now propagate back, thanks to differentiable rendering, all the way back to my 3D shape. And this very simple optimization approach allows me to lift objects to 3D, and also gives you an idea of how differentiable rendering can be so critical for 3D understanding. And so some results of this approach, which is purely optimization-based, taking 8 input views of whatever this object is, and lifting it to 3D, and understanding both the shape, the geometry, and the texture. Also working with real products. We took some Amazon images of people selling their items. This is a guitar, 4 views, and we can lift it to 3D. And even statues. So these are some views of a horse statue somewhere in the world, and how from these few images, we can actually get this more detailed shape and texture representation. So this one, as I said, optimization-based, multiple views to 3D. But what if I don't have multiple views? What if I only have one image? Is this possible to actually reconstruct the 3D structure of the object that I see from just one image? And why one image? Well, one image is important because it is more application friendly. One click. I would like to understand the world by one click of my image, of my scene. Here's my image, and then understand everything in 3D from that image. By the way, how many of you are aware of this object right here? Right. It shows the generational gap. So this is spiral. So image to 3D, we would love to reconstruct any of these objects, that being spiral, or that being any object, even object that we might never have seen in the world, like these imaginary object by Dali, a marshmallow with in the shape of a cat with a mustache, or a capybara with a hat. These are definitely going to be out of distribution from my training data, but I would love to be able to reconstruct them. So this problem formulation right now suggests that we now need learning. We need to bring the big guns of learning because we have one image and we also want to build generalizable systems to understand in 3D. And the way that we decided to formulate this problem and turn it into a learning problem is as follows. So this was a paper that we presented this year at CVPR. So we take a single RGBD image of the object. Why RGBD? Because it's RGBD cameras are everywhere. If you have an iPhone, it's right here. So it's very easy to capture RGBD images today. So we start from this RGBD image. This is the RGB part, and this is the point cloud part. If you unproject the depth image from that, and as you see, half of the object is missing. So what we do is that we want to get to the full 3D structure, and to do that, we train this encoder-decoder network in 3D space. The goal of this network is to complete the 3D shape of the object, and so that it reconstructed in its completion. And it's actually going to do more than that. It's also going to clean up the input 3D representation. And how we're instantiating that is with modern learning and modern neural networks. So we take our image and we use a transformer network to embed it. We use transformers. We use the VIT architecture, which is the most powerful architecture today to embed images with. We do the following with the scene point cloud, the unprojected depth from the RGBD view, where we use another transformer model that now takes as input the XYZ points, which are the incomplete 3D representation coming from the RGBD view. Then we use a decoder network that queries in 3D point that network in order for every point to predict whether the point is visible, occupied, and whether it is actually its color. So for every query in 3D space, we predict whether it's occupied or not, and what its color is. And that decoder network is another transformer model. So the nice thing about this architecture is that it needs only point supervision. I only need supervision to verify whether my points are occupied or not. It is class agnostic. There's no class information here. It's just digest any images of any object types. And it's a very general transformer-based design. So there's no priors. We don't need to do anything special. We just take transformer modules that we know are powerful, and we make it into a 3D representation. So we trained this on all the data that was available to us at the time, and especially the largest data set in 3D at the time, which was Co3D. It has videos of over 51 object types, actually 37,000 videos, which results in over 400,000 images. And since there are videos, you can apply structured from motion to get these noisy point clouds that you can start with. So here's what I'm going to show you what the results on training on Co3D and supervised with these noisy point clouds coming out of structural from motion looks like. So first, I'm going to show you results on a held out set of novel objects on Co3D. This is the image of a backpack. We actually held out the whole object type, so we never trained on backpacks. So the model has never seen what even is the concept of a backpack. So this is the input view, the depth view. So you see that you only see some part of it from the view of the image. And as you see, the point cloud is actually noisy. That is because we can never assume that RGBD images will actually be accurate. And this is our reconstruction. So it reconstructs the full object shape. In addition to that, also cleans out the points that were mistakenly used as input into our network. Results from iPhone capture. So we took our phone, captured our favorite object, for example, Spyro. So what we use here is the depth from the lidars, from the iPhone's lidar camera, which, as you see, is also leads to some inaccurate points. And our model is able to reconstruct the whole shape, but also clean out these points. Another one of the objects in our house was Zuckerberg's favorite toy, though he wishes it was more popular than that. So RGB image, and this is a fantastic object because it doesn't resemble anything else. Actually, it's a very uniquely shaped object. So, and you see how the iPhone's LiDAR camera is not doing a fantastic job either here, but the completion does. Some more objects from our phone, and some DALL-E-generated objects. Here, the depth that we use is we took an off-the-shelf depth estimation network to give us the RGBD images. So this also showcases the generalizability of this model to any modality in depth, any way to compute depth. So you have your marshmallow, whatever off-the-shelf depth estimation network will give you, which only corresponds to the depth in the view, and then the completed shape. A capybara with a hat, similar results. And I can show, there's much more results to show. You can go to the website of the project and see a lot more of those. This is a difficult task, image to 3D for any object and any shape. It's definitely a challenging task, but it would be great if we could crack it. And some of the limitations of this approach have to actually do with the depth estimation error. We actually found that the biggest error mode is what happens when the RGBD view that we get as input is actually off. So here you see Pikachu, you see how their depth believes that the left ear is kind of extended more than it should be. And you can see why it thinks that. And our model is trying to kind of work with what it has in this case, where it's trying to produce this weird looking ear. That's definitely not true, but it does what it can do best. But one of the most exciting results from this paper, in my view, was when we studied the scaling loss of this approach. We wanted to see how much are we limited by data? What would happen if we had more data? How would the model performance increase? And we found that we're nowhere near plateauing. If we had more data, all of our scaling loss studies suggest that performance will actually keep going up. And this is exactly what motivated us to collect an even bigger data set than what existed at the time meeting 2 years ago. And so with a bunch of great people from UW, from the Allen Institute, and with the help of Stability AI, we collected this data set. We call it Objaverse, extra large. It's a universe of over 10 million 3D objects. Matt, the first author, prepared this cute little video that shows you the diversity of the assets. They are collected from all over the world, trying to have these a spread in what people create around the world and what it enables, what training on such a big data set enables. This data set is out there for everyone to use, and pre-trained models are also out there. But understanding objects is one aspect of scene understanding, and all of now in this chapter of 3D understanding was related to single objects. But the world is a lot more complex than an object in the foreground. The world looks like this. You have a scene, you have many objects. They are diverse, they are laid out in various ways. And it would be great if we couldn't only understand the single objects in that installation, but we could also understand how these objects actually relate to each other in a scene, how they're positioned in 3D space. So from one image, could we understand how all of these objects are laid out? And so that was the next challenge we wanted to tackle. So we wanted to get from an image to understanding 3D objects and laying them out in 3D space. So what you see here is bounding boxes on the 3D objects and their types, but also their location in 3D space. This is a top-down view of what the model thinks the model that I'm about to present thinks these objects are laid out. So if single object 3D understanding wasn't difficult, now we're talking about like challenges that made us actually bang our heads against the wall all the time. And so we worked on this project for over a year, trying to figure out, it's the Omni 3D project, and I'm showing the authors here because there was a lot of sweat involved in making this project. So first, just to frame the problem, we were inspired by the most popular problem in 2D recognition, which is 2D object detection. Is what I showed you earlier today on the video with Masker CNN. The problem of 2D object detection is you're taking an image like this, and this image can contain any object, and you want the output to be all objects that appear in this image, their object types, their location, their XY center, and the width and height, their size, their dimension, and all of these attributes in pixel space, this convenient, wonderful 2D grid that makes life easy. Now, 3D object detection extends this problem. It extends it by requiring the model to detect all objects, just like before. But now, every object that has its category label like before, but now is described by 3D attributes. It's XYZ center, its width, height, and length, and its pose. And all of these characteristics now, they're in metric space, this continuous 3D space, which makes life hard. So this is the problem. It's a challenging problem. So the first thing we had to do in order to get working there is we had to establish a data set. Learning from data is important, and we want to have data that allows us to learn exactly for this problem. So what we did through a very creative process, we figured out how to get you a data set that is large scale and diverse in both object types and scenes. It has over 3 million object instances annotated with all of these 3D characteristics. It is 20 times larger than any other data set for this task before, so it enables a lot more understanding for diverse objects and scenes with over 97 object categories. So this data set, the existence of this data set now allows us to train neural networks that could tackle these tasks. But, and we did that. And jumping to the result, it was great. We trained this model that we call CubeRCNN. We're not very creative with our names. There's a lot of RCNN involved. It's a marketing strategy, but CubeRCNN, it performed best on Omni 3D, which was great on this bigger data set. And through this exercise of trying to create this general 3D object detector, we also found that it performs best on even other data sets that were before used for this task. So one model turns out that if you train it with generalization in mind, performs best than even prior attempts that were specialized for specific data sets. But what's more exciting is not the performance in these bars, though reviewers want to see them. It's actually the results. It's the fact that you can now take this model that was trained in Omni 3D and you can deploy it in any image out there. That was not before the state of affairs in this problem. Before, generalization was not even something that we could think about. But now, because we have this bigger data set and we have this more general model, we can take any images from the web and we can actually understand and predict 3D objects. So very briefly, CubeRCNN, what it looks like, it's actually very simple, almost embarrassingly so. So you have an image. You use your favorite neural net. It can be a CNN, it can be a VIT, whatever comes next. It's a meta architecture, so we don't really care what a neural network is. You can pick your favorite, and it doesn't matter. So the output of that neural net is a feature map that embeds the input image. Then, following the RCNN framework, and I'm sorry, I'm getting a little bit more into the details. The first output here is detecting regions. So this is where the model places 2D objects about where it thinks objects live. Then follow the 2D and the cube head. So the 2D head detects objects in 2D, and the cube head, which is where CubeRCNN comes from, lifts these objects into 3D space by predicting their XYZ center, their width, height, and length, and also their pose. And the output of this is this bounding box, which we represent as a point cloud. And then we apply a point cloud loss with a 3D ground truth in order to train the model. Now, the reason why everything is so simple and almost there's no intricacy in the models because we actually worked hard to make it. Our goal here was to build a model that anyone can use and build upon and extend and not make it complicated and inefficient. And so in order to make this model performant but also simple, we had to innovate in all of these ways. It was a struggle after struggle after struggle, but we succeeded in overcoming all of these challenges, and all of these challenges are actually very important. Actually, every one of these challenges is one lecture, one class in the class that I'm teaching at Caltech, describing each one of them because they're fundamental challenges going from 2D to 3D, and overcoming them is actually is not clear. This is 1 out of 10, but there is a lot more there, and it's something that I want students to be thinking about. So I'm not going to go into the details here, because I don't want to bore you, but a lot of them are in the paper, written in the paper with a lot of extensive discussion about how we went about them. And I want to take you straight to results. Here are some, I want to show you images, predictions of our QBR-CNN on various images of scenes. So what you see on the left is the image, on the middle is the 3D bounding boxes that the model predicts, superimposed on the image, and also a top-down view. When you want to look at 3D results, you always need multiple views. Otherwise, you don't really know what's going on. And this top-down view shows you, it puts the object on top of a grid, and every little grid here is 1 meter across 1 meter. That shows you the scale, which is something that we actually need to predict as well. So another scene. An urban scene, because this is a community where you want to make the self-driving car people happy as well, that your model works. And also from random images that we drew from the internet. So this is someone's living room, I think from Reddit. I don't know where we took this image, or a street scene right here. We also use this model for seeing if we can use it in AR and devices. So we took that AR headset that Meta has created. It is the Project Aria headset. So it's this nerdy looking, though fascinating hardware. You put it on and you can walk around, and this is what you see here. This is a video of someone walking around in this apartment full of Facebook employees and looking at the scene. And so so one challenge we wanted to convince people, hey, this is cool, you should use this. We took QBR-CNN and we ran this frame by frame on this video. So this is frame by frame, where there's no temporal information used here. And as you see, the model is actually predicting the objects and placing them as it goes. Nothing is solved here. There's a lot more room to improve, but exciting result nevertheless. So tons of limitations. The first limitation is that we still see modes where the model fails, especially when the configurations are less common. In this example, where there's a car basically inside, like on top of another car, the model really doesn't like that. So it's trying its best to not predict that. Also, the fact the biggest error mode is in depth. So failing to predict accurate metric depth from an image. You'll say, are you crazy? How are you predicting depth from an image? Yes, it's a hard task. We rely on priors, but it's doable nevertheless. And one way that we thought of actually framing this in a more well-defined way is no longer depending on images, but on videos. So videos should help us disambiguate depth. And this is exactly what we did in this project at ICCV, where we now take a few more frames on a walkthrough of a person walking around, and we're able to detect objects in 3D, and it turns out that actually minimized the error in depth. More details in the paper. This was done by Yiming, who is brilliant working in 3D and graphics. And the other limitation is that we only support close world vocabulary. So we have a set of object categories, and that's what we support in QBR-CNN. And it would be fantastic if we actually could lift that constraint and extend the capabilities of a model like QBR-CNN, or actually any model that was trained in a closed vocabulary setting, to an open world vocabulary. And this is where this idea of the findings in large language models and how we can possibly bring large language models into this by extending to more than one categories. And so talking about LLMs, obviously, I can't give a talk on computer vision without acknowledging the fact that they're out there. And actually, they're quite impressive. So LLMs, you know it. Turns out that how most people want to interact with LLMs is by chatting with their favorite celebrities. So there's chatbots out there that are based on large language models and that take characters. This is Character AI, like likely the most successful startup on LLMs. Sad in my view, but it is what it is. The world. However, there's actually exciting technology, and I wish people see, and I'm sure that we all see that, but I wish also the public saw that there's actually these models are having amazing perception capabilities to the point where all of us computer vision researchers are actually amazed. You can upload an image of a flower that you see out in your walk, and you can ask what the species of that flower is, and it will tell you, and actually will tell you accurately most of the time. This is an impressive result from a vision perspective. This was a fine-grained classification challenge, which is something that we were working hard. I wasn't working on this problem, but a lot of my colleagues were. And now you have a model that wasn't even thinking about fine-grained classification, and here you go. It does well. And of course, it does well in any sort of understanding of what is contained on images. But, and this is putting my science hat on, it doesn't solve all the problems. They are fascinating, they're fantastic, but when it comes to grounding, which is everything I discuss about today, these models start failing. You ask GPT-4V how many donuts are in this image, and it will tell you there's 6. There's clearly not 6, but you run a model like Mascarcinin and will detect all the donuts accurately. Why? Well, this is because these questions require grounding, and this is not how these models were trained. These models were trained at an image level. But we do have solutions to ground to actually detect objects. They're not there, they're not part of them as of now, but they will likely become. And obviously, these models are also not very good at perceiving in 3D. You can ask 3D related questions on this scene to GPT-4V, like I asked it, which object is nearest in depth? Is it the pedestrian, the motorcycle, the silver sedan? It will say the pedestrian likely did like a random draw. Well, clearly that's not the case. Then you can have a model like CNN, which actually will tell you which one is closest in depth. So all I'm trying to say is that there isn't a golden solution right now in perception. We've made tremendous efforts in all of them, and always be critical about what you think the capabilities are in each of these models. And so to summarize, I want to say the following. So I took you to this journey starting from the 1970s to today, where this was the journey of transforming Pixel to Percepts. It's been a long journey, eventful, and still ongoing. The biggest lesson, the most important lesson in my view, started in the 1990, which was learning from data. That is the one lesson that's still relevant to this day, and the one lesson that we know works. And it's a lesson that I think we'll keep applying. However, it would be great if we could learn from less data than the current demands. It feels kind of absurd that I need actually 1,000 examples of a cat to learn the concept of a cat. I, as a human, can learn what a cat is or any other new concept very efficiently. So learning from data, yes, it would be great, though, to learn from less data. And from now until I think the future is the time for 3D and 4D. We've had great successes in the 2D computer vision. We actually have most of the solutions there. I showed you. Now it's a matter of bringing them all together to build a big model that does all. But how do we go to 3D? How do we go to 4D? The world is dynamic and it moves. These are still very much open-ended problems, and we don't have solutions to them. But if we did, we would actually enable all of these embodied and robotic tasks we would so much like to have. I'm sick of doing dishes. I want someone else to do them. So without that, I think this summarizes how I think about this journey from pixels to percepts. I hope it was an enjoyable talk, and you learned a little bit about what was going on. And for the remainder, I think I have a few minutes. If you have any questions, happy to answer them.
Thanks so much for that amazing talk. We definitely have plenty of time for questions. I think we need to make sure we get the question in the mic for the benefit of the online participants. So I guess I'll just kind of walk around and.
Okay. Thank you very much for the nice talk. I also use like Observers already in a project, so really nice to hear a talk from one of the authors. I have one question regarding the reconstruction from a single image. So you said for training you used like the structure from motion point cloud, but I was wondering if not using a depth estimator completely would solve some of the problems, because for structure from motion you also need multiple images,
Right.
which is the idea to not do with the single image reconstruction, I think. So why not using a depth estimator which produces nice and crispy images compared to the sparse?
Is your point to use a depth estimator to get better structure from motion outputs, or for the single image, for the single view understanding?
For the single view, so just throw away the structure from motion and maybe also the LiDAR point cloud. But if you work with a single image, then the scale of the object is anyways a complete different story. So
yeah, I agree with you. You should be moving into RGBD, and I wish there is more actually data sets out there with RGBD with a depth modality. But LiDAR is not going to solve all of 3D for you. It's that any depth camera from a single view will only give you what you see from that view. Everything that is in the back, as I showed you with the MCC work, you won't get. And you will have to complete. Like in the spiral image, a depth sensor will give you what it looks like from the front, but the complete 3D shape is not there. Does that make sense?
Yeah, but it's also not there. It's never there. So
it's never there. So this is where learning comes in, and this is why learning completes it.
Yeah, I understand, but why not using depth estimation for the input and forget about the structure from motion point cloud?
Oh, because we need to supervise MCC with the whole. So when you supervise these methods, you want to supervise them with the whole 3D shape.
Okay.
This is where structure from motion comes in. You have these videos, so you have a complete point cloud, which now you use for supervision because you want to get from incomplete to complete.
Okay, thank you.
Thank you for your talk. Unfortunately, I was not able to attend the first part when you talked about Observerse. I would have loved to hear more about it because we use Observerse as well. But I'm actually going to talk about the issue that you brought up with the single image, where we still have a hard time resolving the scale problem, right? And that's where I don't support the idea that you can use depth images. Sure, but the hardware for depth is fairly expensive while cameras are still. So what should we be doing there? I think that annotating large data sets with scale would be nice, but how to get to that point?
Yeah, I agree. So depth is a curse and a blessing. You said it's not. First of all, they're not accurate. Even the most modern LiDAR cameras have one range, and beyond. Actually, in the scenes that I showed you in Cupertino, the urban scenes, no, I don't think there is a camera today that's commercially available that will capture the depth all the way 200 meters in, which is what some of our objects are. So I agree. This has been data has been the biggest limitation in 3D, which is why most of my talk today was like, we need data. And after we get data, we'll get the model, but we need to figure out what our data is. I don't have a solution about how we're going to scale it. We might have to get more creative than 2D. The recipe that was successful in 2D, which will get a lot of people to annotate and pay them some money, might not scale in 3D. So we might have to get more creative. And this is a great opportunity for research and ideas to come in, not just in the modeling side, but also in the data creation side. So short, my answer is, you're right. I think this is what we as researchers, this is what we need to figure out.
Wonderful presentation. Thank you. I really enjoyed you highlighting the 2D features inside of the object recreation and the detection. How would you go about extracting features for your 3D models?
Yeah, so we have 2D features whenever we have only one image available, because that's so a big part of 3D is utilizing, or how I've been going about it is trying to figure out how to utilize the best I have in 2D so that I can build on top. I don't want to reinvent the wheel. I want to be able to use the most powerful 2D representations. And so 2D feature is always going to be relevant, because these feature representation methods are actually in 2D getting very good. So they should be useful. In the project where we had a video input, so we had multiple images, we actually did extraction in 3D, where we put the features in a 3D space coming from all of these. So images, 2D features, and then these features are unprojected in 3D space and now live in a 3D space. This is what we did. I don't think it's the best idea. I think that, again, this is open for debate and open for research, how to best lift your feature space to 3D, if even you want to lift, or maybe you want to start from 3D and then project to 2D. So these are all like open challenges and open directions, and definitely part of what we need to investigate to make 3D happen.
Thank you.
Thank you for the presentation. And since this is an AR event, I will like to know, like, where do we stand from this 2D to 3D if we want to do markerless interactions for accurate
Markerless interactions, interesting, yes. So do you mean where we stand? So what is markerless interactions? I just want to make sure that, because I think I know, but I want to make sure that.
If you want to place some virtual objects with your any AR device, and
I see, yeah. So this is what I call embodied. For us, more computer vision, I think that's what we call embodied. Okay,
Yeah.
okay, got it, yeah.
So if you want to have accurate placement, because when you show 2D to 3D, there's no measure of accuracy there. But if you want to work with AR, you want accurate.
Absolutely.
So
if you want to work with AR, you want to accurate. I have all the roboticists at Caltech that keep yelling at me. It's like, I can't make these shapes they're not useful. I want to manipulate the object. I want my robot to touch it.
yeah,
Agreed. Correct. So this is why this is why there's so much more work to be done to get to a place where 3D is useful. And that's what I like about 3D. It's like it has a direct application. When we were working on 2D, it was more like an academic mental exercise, like, can we recognize objects? The application, I think there's a lot of application in e-commerce where who cares if you're not very accurate, if you detected the backpack accurately or it's a little bit off. E-commerce will use whatever you give it. But with more embodied applications like robotics, like AR, you need accuracy, and that dictates what we need to do. So this is why I'm more excited about this space, because my applications dictate how far I need to push. And I agree, we're not there yet. And whether it's going to be learning AI, whether it's going to be optimization, whether it's going to be better hardware, I think all of that together. The roboticists need to step up their games with the hardware that they use. I think the AR folks need to also do that, especially make these headsets better, less. Yes, I mean, they're great. I don't want to offend anyone with their headsets, but I've used them, and it would be great to, once the hardware is in place, I think that the software will come in place and the learning will come in place, but I think it's going to be all of these communities coming together, which is fascinating. I hope we make it work and don't. Fine.
I had one question.
Yeah.
You talk about meshes and point clouds. I was wondering what you think about the potential for like volumetric representations or Gaussian splatting, or these new kind of representations coming out from view synthesis, the potential of that for learning.
Right. So that's a great point, and I do have a class that I'm teaching actually today later exactly on that. So the other beautiful thing with 3D is that depending on what you want to do, it turns out that maybe you want to take a different approach. If you care about creating beautiful images, maybe you want your NERF or your Gaussian splatting or whatever the modern version is. I am yet convinced to see that any of these representations is good for more embodied interactive tasks. You know, if my roboticists are not happy with the 3D that we create, I think that giving them like a smoke representation will make that less appealing. But you know, we're building tools to enable various things. So what it is that we enable should dictate what our approach is. But I'm a big fan of these. They're so elegant, so easy to use. You no longer need to know all this intricate rasterization stuff, which was a pain in the ass. But yeah.
Thanks for the amazing presentation. So tagging on the interactivity questions. So one aspect of that is obviously performance. So where are the inference times right now in your work? Because you didn't mention it. And I'm also obviously interested in the resources needed for the training of these massive endeavors. But inference is probably close at heart for this community.
Mm-hmm. Yeah. So these are great questions that you're asking, and this is where all of us learning people need to be embarrassed because nowhere near real time. To train, you need to spend $200,000 in GPUs to even get to half of the GPUs that you need to train. So the demands are many. And this is the curse with also going to using these more powerful transformer models because they're even less efficient. We're moving away from real time as opposed to getting closer. But there are things that you can do to make things efficient. So this is like, you can amortize the cost of various computations, sending some computation off to be done by a cluster and then querying. So for example, in the image to 3D shape, you can get that representation out of the image once, and then you can query your 3D representation in a different part of the network. Well, the first one has already been computed. You can iterate on that. So there could be efficient things that you do. But if you're asking, can this happen on a headset or on a robot on its own, standalone? No, not yet. If you had Wi-Fi, if you could send data over and you didn't care about that latency very much, still no, but yes, I guess no, I'm just in denial. Yeah.
Maybe just one last question before we go to the break. You started with the connection to the human visual system, and I wonder if if you're still looking to that for inspiration, or you think there's something we should still be doing that. I feel like with Transformer, we've kind of gone away from it, which is a little sad for me, but yeah.
Yeah, no, this is always a topic. You know, Caltech has a big neuroscience department, so this is if I feel like I want to pick a fight, I go there because like they think that everything we're doing is wrong because there's no connection to the brain. I agree. For me, the inspiration of so I'm inspired by what we can do, and this drives the inspiration. Whether how we do it will replicate or emulate the human brain, I don't think it's necessary. This is what I tell them. I don't have billions of years of evolution to like evolve our like the human vision system has. So we will have to take a shortcut. I am though very unhappy with the fact, and going back to how we learn, one thing that I feel, I don't care about whether it's Transformer or something else that doesn't have a connection to the brain, but I find the limitation of having to learn from billions of data points a very embarrassing state for us to be in. We should be able to learn more efficiently with a few examples as opposed to having to train these multi-$100 million models and requiring a lot of data. So how are we going to get there? This is why we're overworked.
Excellent. Well, thank you so much. Let's thank Dr. Gkioxari again. Thank you so much. I hope you can stay a little bit to hang out before your class.
Yes, yes, yes.
Thanks so much.
Thank you.